The ninth problem in our hand is another pretty interesting problem of ionic equilibrium. We have a 40 ml solution of a weak base BOH which is being titrated with 0.1 normal HCl solution. The pH of the resultant solution has been found out at two different times. First, when 5 ml of HCl has been added, the pH is 10.04, and when 20 ml of HCl is added, the pH comes out to be equal to 9.14. We need to find the dissociation constant for the weak base. Now let us consider the reaction between the weak base and the strong acid HCl. BOH plus HCl undergo the neutralization reaction to form BCl plus H2O. Consider the case first when 5 ml of HCl has been added. So the number of millimoles of HCl is 0.1 into 5, that is 0.5 millimoles. And for BOH, let us consider the initial number of moles to be equal to A. If HCl gets completely reacted, we have A minus 0.5. This gets 0 and this becomes 0.5. Mind you, these are the number of millimoles of BOH and BCl. So in the final resultant solution, we have BOH and BCl present. This is a weak base and this is its resultant ion or the conjugate ion. So there is a base and a conjugate ion present in the resultant solution. Hence we have a question of buffer. The pH at this moment is given to be equal to 10.04. Hence its POH will be equal to 14 minus 10.04, which is equal to 3.96. This is equal to pKb plus log of salt upon base. Here the salt is BCl, that is 0.5 upon the base, that is A minus 0.5. Actually we need to take the concentration, but the volume for the flask is 40 ml, and hence when we divide this by 40 and this by 40, the 40-40 factor gets cancelled, and hence we can take the ratio of the number of moles present at equilibrium. So this is our first equation. pKb can be further written as minus log Kb. This is a dissociation constant for the base, plus log of 0.5 upon A minus 0.5. This is our first reaction. And for our second reaction, we have over here the pH is given to be equal to 9.14. So the POH will be equal to 14 minus 9.14, which is equal to 4.86. The reaction goes as follows: BOH plus HCl becomes BCl plus H2O. The initial number of moles of BOH, let it be equal to A. Now HCl added is 20 ml. So the number of millimoles of HCl is 20 into 0.1, that is 2 millimoles. Let the initial number of millimoles as before was A. This is 0 and 0. This is case 2, when 20 ml of HCl has been added. When this HCl completely reacts, the left millimoles of BOH is A minus 2 and this is 2. So again we can apply the buffer equation to be equal to POH, which we found out to be equal to 14 minus 9.14, that is 4.86, is equal to pKb, which is equal to minus log Kb plus log of, again salt upon base. Our salt over here is 2 and our base is A minus 2. This is a second reaction, or rather the second equation. On solving this first and this second equation, we get the value of Kb as 1.81 into 10 power minus 5. And hence our final answer for the dissociation constant for the weak base is 1.81 into 10 power minus 5.